So let's talk about London dispersion forces now. The motion of electrons around the nuclei can temporarily lead to polarity. One thing you have to keep in mind is if you have atoms and molecules, electrons are always going to be moving around the nuclei all the time, really fast. In fact, so fast that it's convenient for us to just imagine the electron as just like a blur or a cloud around the nuclei, right? But because they're always moving, at any particular instant, it's possible. It's very likely that you can have what's called temporary or momentary polarization. If you were to take a snapshot of your molecule at any one particular instant, you might find there's a higher concentration of electrons on one end of the molecule versus another. So because of this temporary polarity, so you say that your molecule has what we would call fluctuating dipoles. They're not like polar molecules where you have a permanent dipole. Molecules in general, even though they're non-polar, they can have what we call fluctuating dipoles or momentary dipoles or instantaneous dipoles. So you can have attractions between these interactions, between these fluctuating dipoles, and so that leads to attractive forces, even though molecules are non-polar. Okay? Now, larger molecules, the bigger the molecule, okay, the more likely you have the stronger these fluctuating dipoles are going to be. So we say that larger molecules are more polarizable. So you would expect stronger London dispersion forces between larger molecules. Okay? So for which of the following pairs of molecules are the attractions due to London dispersion forces stronger? Between a pair of CH4 molecules or between a pair of C2H6 molecules? Very good. C2H6 molecules are larger than CH4, so they are more polarizable. So you would expect to see stronger London dispersion forces among them. You can just say dispersion forces or London forces or London dispersion forces. They all mean the same thing. Okay. So for which pair of molecules is London dispersion strongest? Between a pair of water molecules, between a water molecule and an H2S molecule, or between two H2S molecules? So you have to go by size, right? So where is what oxygen and sulfur in your periodic table? Group 6A, column 16 of your periodic table. You have oxygen in period 2, sulfur in period 3. What's the trend in size going down a column? Atomic size increases. So which one would be bigger, H2O or H2S? Okay, in terms of size, water will be smaller than H2S. So for which pair of molecules is London dispersion forces strongest? Between a pair of water molecules, between a pair of H2S, or between H2O and H2S? Okay, correct answer is between a pair of H2S. So you would think that H2S molecules would have stronger attractions for each other compared to water molecules, right? So based on this alone, you might say, which one would have a higher boiling point, H2O or H2S? You'd think H2S would have a higher boiling point. They have stronger attractive London dispersion forces. But water is a strange creature. It's a strange molecule. It has a much higher boiling point than H2S. H2S is a gas under ordinary conditions. Water is a liquid. So water molecules have much stronger attractions. And the reason for that is there's another source of attractive forces, and another reason why water molecules attract each other, and that's called hydrogen bonding interaction. We'll deal with that in just a short while. But based on London dispersion forces alone, you would think the H2S would have stronger attractions for each other than water molecules, but that's not the case. Okay? But if I'm only asking for London dispersion forces, then the answer would be H2S. Okay? But overall attractions, it turns out water molecules have stronger attractions among between them than H2S molecules. All right, so let's take a look at this one. Which of the following has the lowest boiling point? O2, F2, or Cl2? Where do you find this in your periodic table? Oxygen, fluorine, and chlorine, right? That's how you find them in your periodic table. Fluorine and chlorine would be in group 7A, oxygen is in group 6A, and oxygen and fluorine would be in the second row. Which one would have the lowest boiling point? What are we trying to look for here? Weakest attractions, right? Weakest attractions would give you the lowest boiling point. So do you have weakest attractions among O2 molecules, or among Cl2 molecules, or F2 molecules? Okay. See if you remember your trends. What's the trend going left to right across the periodic table? Increasing or decreasing? Decreasing size, right? So fluorine is smaller than oxygen. What's the trend in size going down a column in your periodic table? Increasing size. So fluorine is smaller than fluorine. So the answer is fluorine. Oh, you need to review your periodic trends in atomic sizes, okay?